Welcome to lecture number 14 for ECE 321 Analog Electronics, Common Emitter Amplifier. Now, where we're at is in the previous lectures we looked at taking a transistor circuit like this, finding the resistors to bias you in the active region. So again, if you draw the load line for VCE versus IC, it's going to look like this. I chose RE. Well, RE is not 0. That allows me to stabilize the Q point. I chose R1 and R2 so that the Q point is stabilized for variations in beta, and chose them so that the Q point was at 6 volts, right in the middle, and this is 12 volts. What I'd like to do now is use this as an amplifier. What the capacitors do is they isolate the circuit at DC. So what I'm going to do is for common emitter amplifier, take this point and tie it to ground. I'll have this go to my input. And here's my output. Say it goes to an 8 ohm speaker or some other load, probably like a 1K load. How does this circuit behave for an AC signal, also known as a small signal model? If you look at all the voltages on the circuit, again, the voltages, say right here, we'll have some DC signal. On top of it, I'll have a small AC signal, like 1 millivolt at 1 kilohertz coming in. The output right here at the collector will also have some DC offset. Plus, it'll have the sine wave, the 1 millivolt, amplified in some way. Come up with a way to model this circuit in terms of the AC characteristics. And that'll be the two-port model, or also known as the small signal model. So that's where we're heading. So starting out, there's kind of 3 ways you can connect the circuit. I can take the emitter, tie it to ground, the base, tie it to ground, or the collector, tie it to ground. That gives you 3 different amplifiers. The first one we're going to look at is the common emitter amplifier. Take the emitter, tie it to ground, input goes at the base, output goes at the collector. What's the resulting 2-port model? Well, again, what we're going to do is do 4 different tests to find the input impedance, input gain AI, output impedance, output gain AO. But this circuit's kind of hard to analyze, so it would kind of help to redraw the circuit. And one problem I'm going to run into is there's a diode in the circuit. Again, right here, there's a diode. So if I take this voltage right here and perturb it, how much does the current change? And that's important because the transistor is a current-controlled current device. I need to know the current base to emitter in order to find the current collector to emitter. And in this case, an ideal diode model doesn't work. The problem with an ideal diode is the VI characteristics look like this. It goes to 0.7 volts and turns on. So if I were to take the voltage right here and vary it, the current is 0 or infinity. And that's not really what happens, so the ideal diode model doesn't work. Instead, we're going to take a Taylor series expansion out to 2 terms, which is a highfalutin way of saying, instead of treating this just like a straight line, that'd be the first term in the Taylor series expansion, take it to 2 terms, and say that the voltage is A times I plus B, a straight line, rather than just, previously we just said the voltage is a constant. That was 0.7 volts. That's the ideal diode model. We're now going to use a piecewise linear model, Taylor series expansion out to 1 term. Really what you're doing is you're drawing the tangent to the curve. So, well, one problem you have is that the tangent depends upon where I am on the curve. So I need to know the DC operating point. That's my Q point. The AC model then will be draw a tangent to this curve at that point. Once I have the tangent, what I can see is that as the voltage varies slightly, very small change in voltage, that'll produce this much change in current. And the slope, the resistance, is how they relate. So what I need to do is I need to find out what is this term in the Taylor series expansion. Well, I know from diodes the voltage is NVT times log of ID over I naught or IDSS plus 1. Take the derivative. The resistance is change in voltage with respect to current. That's the full derivative with respect to current of this guy. The derivative, the derivative is roughly, since this is going to be much, much bigger than 1, ignore the 1. The derivative of log x is 1 over x. Here's my pen. So this is going to be NVT times 1 over x, which is I naught over ID, times the derivative of the inside, which is 1 over I naught. So these terms cancel. ID is the current through the diode at DC. That's the previous analysis we did. I've got to do the DC analysis to find out what is the current through the diode. That's important. That tells you the slope. NVT is just a constant for a given transistor, or given diode, given transistor. So if NVT is 0.026 and my Q point is 30 microamps, RF is 867 ohms. That's your slope. And note that this equation only applies to diodes. In general, the slope is the tangent. So if we had some other function, I'd have to recalculate the derivative to find out the derivative of the slope at that point. For diodes, you have this. So, now that I know the resistance of a diode, I can draw the small signal model. So suppose I have this circuit right here. Based upon my DC analysis, I know the current in the diode. From the small signal model, I know that this is 867 ohms. Find the two-port model. So what we'll do is I'll redraw the circuit. And the way I like drawing the circuit is here's your input. Let's start from VN. Let's scroll down a little bit. So here's VN. Yeah, let's do it this way. Here's VN, and here's ground. From VN, I assume that this impedance is small. So this is 1 over j omega c. It's maybe like minus j 100 ohms. 100 ohms relative to 17K is small, ignore it. So at VN, I go to the base, right here, there's the base. I see R2 to ground. I see R1 to ground. And that takes me to my diode. The diode is RF. There's your base. That takes me to the emitter. And I find it really helps to label the nodes. At the emitter, emitter is tied to ground through that wire. And let's see, the emitter is also tied to the collector through beta IB. This is also the emitter. 200 IB. IB is the current based to emitter, so that's IB. And the collector is tied to 12 volts through RC. And 12 volts, this is actually 12 volts plus 0 sine omega t. We're doing the AC model, AC analysis. At DC, this is 12 volts. At AC, this is 0 volts AC. It's a constant, it's not rippling. So for AC analysis, that looks like 0. So that goes to ground. So there's your circuit. And this guy right here is the collector. Redrawing it, I can draw it like this. And what really helps in this class is the original circuit is kind of confusing to analyze. It's what you build, but it's a little bit hard to analyze. redraw it. If I redraw the circuit, I get this one right here. That's a lot easier to analyze. Now that I have that circuit, find the 2-port parameters. So what I'm going to do is looking in, what do I see? What's the Thevenin equivalent? At the output, what's the Thevenin equivalent? So, given this guy, looking at the input. Looking at the input, it's pretty clear. I see R1 in parallel with R2 in parallel with RF. So that's Rn. And there is no voltage source over here. So AI equals 0. Doesn't matter what you do to the output. If I put a voltmeter right here, I'm going to get 0 volts. There's nothing driving it. So that's half of the 2-port parameters. For the other half, I'll look at the output. To find R out, I short the input. That makes this equal to 0. That makes this equal to 0. All I see is RC. So the output impedance is just RC. To find the output gain, what I'll do is I'll apply 1 volt at the input. Then this current is 1 volt over RF. This current is 200 over RF, 200 times bigger. And then the current, this is the direction of current. This voltage is I times R. That voltage will be RC times 200 over RF. Relative to V out, the polarity is backwards, so the gain is actually minus. So the A out is minus beta times RC over RF. And there's your 2-port model. And summarizing it, I can simplify it like this. That's what she looks like. Notice this is a whole lot simpler to analyze than what we started with. That's the reason we like 2-port models. It really simplifies the circuit, and in terms of characteristics, it behaves exactly the same. In Circuit Lab, I can check. Suppose I build this circuit, I want to find the 2-port model. Well, to find A out, well, if I look at the different signals, if I have, this is a 1 millivolt sine wave, all the voltages in the circuit have a DC term, that's the DC analysis, plus an AC term, that's the ripple, that's the AC analysis. And by superposition, I'll have 2 terms, DC plus AC. The capacitors block the DC, so all I really care about is the AC part. So to find the different parameters, what I could do this is DC analysis, okay. Build the circuit, find the DC terms, and it's about what I expected. VCE is about 6 volts. I can find the current IC, find the current IB, find beta. For this transistor, Circuit Lab assumes beta is 151. And then RF is 677 ohms. To find the output gain, what I would do is apply a 1 millivolt sine wave, 1 millivolt at 1 kilohertz at the input, measure the voltage at the output, and what I get is the output is 203 millivolts. So the gain is 203. And a minus sign, if you check, when this is plus, the output is actually minus, 200 times bigger. So the gain is actually minus 203. I calculated minus 230. Again, a little bit different because beta is different, but close. And again, the gain is beta RC over RF. So if the Q point is slightly different, that changes the gain. If beta is different, that changes the gain. Beta that Circuit Lab uses is 150. We assume 200. So there's likewise a slight difference in gain. To find the input impedance, what I'll do is I'll add a resistor in series. I chose 605 because that's what I calculated. Make the output impedance large. measure the output voltage, and the output voltage drops down to 95 millivolts. Without that resistor, it was 203 millivolts. So that means that the input, since AI is roughly 0, I've got your Rn, I've added 605 ohms. That 605 ohms gave you, by voltage division, this much drops 203 millivolts down to 95 millivolts. Solve for Rn, and you get Rn is 769 ohms, versus what I calculated, 605. Close, but a little bit different. To find the output impedance, I'll take the output, and instead of making it open, making it 1 kilo ohm. What's happening is, from the two-port model, I have this guy. I'm adding 1K at the output, and by voltage division, the voltage will drop. The 1K reduces to 3 millivolts down to 107 millivolts. So I can calculate R out. R out is 898 ohms. And Rn, it'll be basically 0. So experimentally, I can also calculate the two-port parameters. And what you're going to get is the experimental two-port parameters are close, but a little different than what you calculated. Because beta is slightly different, the Q point is slightly different, but they ought to be close. Close like we saw here. Now the reason we're using the two-port parameters is it really simplifies multi-stage amplifier analysis. So suppose I had this circuit. Find the two-port parameters, or find the two-port model. Well, this gets really intimidating. Looking at that circuit, I'd kind of panic and not know what to do. It's actually not that bad. If you look at it, this is actually two common emitter amplifiers cascaded. So here's the first amplifier. Here's the second one. The middle part is all the same. At DC, each of these is isolated. Calculate the Q point for one. I've got the Q point for the other. The first one is a common emitter amplifier. The emitter is tied to ground. Inputs at the base, outputs at the collector. The second stage is a common emitter amplifier. Inputs at the base, emitter is tied to ground, outputs at the collector. So if I take the two-port model for the first stage, it'll be exactly the same two-port models as the second stage, cascade the two-port models. And if I do that, this is what I have. Here's the two-port model for the first stage, two-port model for the second stage. That's actually not too bad. Way, way, way easier than trying to analyze this circuit. And they're equivalent. So, if I want to find the overall two-port model, it's going to look like this. Kind of by inspection, at the input, what I see is 605 ohms. To find the output resistance, if I ground the input, that makes this 0, that makes this 0, that makes this 0, all I see is 1K. The one you got to work for is the gain. So to find the gain, let's apply 1 volt at the input. This becomes minus 231 volts. By voltage division, 605 over 1K, voltage division here, times minus 231 volts, gives you minus 87 volts. Times minus 231 gives you 20,114 volts. So 1 volt in produces 20,114. So this is plus 20,114. That's the two-port model for this circuit. And again, you kind of see that's why we like two-port models. It makes multi-stage amplifiers a lot easier to analyze. If I simulate it, take that previous circuit and simulate it, apply a 1 microvolt, 1 kilohertz sine wave at the input. This is what you see at the output. I get a 1.4 volt sine wave at the output. The gain is the ratio. Gain is 14,000. I calculated 20,000. So again, my calculations are going to be a little bit off. The reason being is beta is different in Circuit Lab than what I assumed. I assumed beta was 200, Circuit lab assumes beta is 151. So the gain's a little bit different. Build it in lab. I'll get another answer. Again, each transistor will have a beta somewhere between 100 and 300. And likewise, each one will have a slightly different gain. But it'll be, same ballpark. So in summary, the common emitter amplifier provides high gain. The two-port model simplifies analysis when cascading at the common emitter amplifiers. The capacitors block the DC offset, so when I start cascading them, one circuit does not affect the other circuit's Q point or DC operating point. And when I apply a sine wave in, I block the DC part of it, so I get a sine wave out also centered at DC. So that's the common emitter amplifier. That's kind of the bread and butter amplifier. If you need a high gain, that's the common emitter. And we kind of saw that a single common emitter amplifier had a gain of about, let's see, what was it? 230. Two of them have a gain of 20,000. Three of them have an even higher gain. So start cascading common emitter amplifiers. I can take a very small signal, like from an antenna, and amplify the bejeebers out of it and get something you can hear. So that's lecture number 14 for analog electronics, common emitter amplifiers.